Welcome to Lecture 15, Series. Intuitively, a series is a sum of infinitely many numbers. That's an informal definition. Formally, a series is an expression of this form. You've probably seen something like this before. This just means a sum, and we're starting at n equals 1. Sometimes we could start at n equals 0 or n equals 6, but this just means take this infinite sum. These are the terms, and we usually write the series, if there's a formula for an, we write it like that, and an is the nth or the general term of the series. Here are two examples. This first one you've seen ever since grade school. 1/3 is 0.3 repeating, which is 0.3 plus 0.03 plus 0.003 and so forth on forever. And you can write that in fractions as 3/10 plus 3/100 plus 3,000 and so forth. Here's another series. I want to ask you, can you evaluate this series based on geometry? I guess the answer is yes, so I want to ask you how. 1/2 plus 1/4 plus 1/8. Let me draw you a picture of what this looks like. This is actually called a geometric series, and it got its name because of this little picture. So the first term is 1/2. So suppose this is a unit square, so that has area 1/2. Suppose this has area 1/4. This is area 1/8. This is area 1/16. And then we can keep dividing this. And it's clear just from the picture that the area of this square is just this infinite series, and so this infinite series equals 1. You can also think of it as like a frog jumping toward a wall. First he jumps halfway there, and then he jumps half of what's his remaining distance, or a quarter of the way, and then half of the remaining distance is 1/8 of the original distance, and so forth. And eventually, so let me draw a little picture. So here's the frog, and here's the frog. Here's the wall. So first the frog jumps halfway, then he jumps a quarter of the way, or a quarter of the original distance, and then 1/8 of the original distance, and so forth. And he'll never actually get there, but as time goes to infinity, and at infinite time, which doesn't really exist, he will have covered whatever this distance is. Let's say that's 1. Okay, so let me give you another example, just sort of for fun. Here's another example. I'm just making up on the spot. N equals 1 up to infinity of. So this one here is 1. This one down here is 1/2 to the n. And this one down here is 1/4 to the n. So this is 1/4 plus, sorry, I wrote 4 instead of n. Let me change that. So that should be an n. So 1/4 plus 1/16 plus, what's the next one? 1/64. So this is a geometric series. Series, as we'll see, like this, are called geometric series. And so I have a question for you. How do you evaluate this geometrically? That's not quite so obvious. So let me show you two ways to do this one. First one, I'll do it up here because I have space. Let's get rid of that there. That's better. So let me take the same square I had before, and let me divide it in 4 pieces. And let me shade in that piece. And let me divide this in 4 pieces. And let me shade in that piece. And let me just keep repeating this. So hopefully you can see why area of this one is 1/4 of the original area. The area of this is, maybe I should use a different color, 1/16. Yeah, so this area is 1/16. This area is 1/4. This area is 1/64, and so on. And so what proportion of this entire square is the shaded area? Now that's not obvious if you're looking at it think of it like this, but look at each of these L shapes. You look at this, each L shape, exactly a third of it is shaded, and the union of all these L shapes is this entire square. So now you can see that that this is just 1/3. So let me circle that, and I'll circle that. Okay, and actually, just for fun, I'm going to give you another way to think about this. So I'm going to do this one in red. Let's take now a triangle. I'm just showing you this because that's fun. And let me divide up a triangle like this. And then let me keep doing this process. So let me shade in. I'll use blue for the. No, I'm not sure what to use. Color. Yeah, I'll use blue. So, oh, that's not blue. Oh well. So let me shade in this triangle. So that's 1/3 of the original. Or that's 1/3 of the big triangles. Now I'm going to shade in one of the. How do I want to do this? I'm going to shade in one of these. And now I want to shade in one of these. And so forth. And I think I said it wrong originally. So this triangle here is 1/4 of the original triangle. So that's 1/4. This triangle here is 1/4 of this quarter of the original triangle. So that's 1/16. This blue piece is 1/4 of 1/4 of 1/4, and so forth. So this thing here has area 1/4, assuming that my triangle has area 1. This guy has area 1/16. This one has area 1/64, and so on. And now it's easy to see that the total area that's shaded in is 1/3, because at each layer, I guess, exactly 1 out of 3 triangles of that size is shaded. Okay, so formally, a series is geometric if each term except I have 2 x's in there. Let me except for the first can be obtained from the previous by multiplying it by a constant called a ratio of the series. So that is, a geometric series has the following form. It's some constant a times r to the n, where r is some number. So it looks like this. And if we want to, we can factor out this constant and write this as r to the 0 plus r squared plus r cubed plus etc. And it really doesn't matter where we start in the series. So depending on the book that you read, this term might be optional. Some series will start at the n equals 1 term, and I guess I should put it 1 here. Although the formula is nicer if we keep in this r to the 0 term here, which is just equal to 1. So it's not too hard to fathom that a series like this is convergent if the absolute value of r is less than 1. So we're adding up powers 1/2 or 1/3, etc. And it's divergent if r is at least as big as 1. So if r equals 1, then we're just adding up a times 1 plus 1 plus 1 plus 1 plus 1, etc., and that's going to diverge. Otherwise, we get something that decreases to 0 exponentially fast, and the thing that I want you to know is this formula right there. That it converges to a over 1 minus r. So in other words, this thing right here, all the powers of r always are going to add up to 1 over 1 minus r. And that's going to hold if r is positive or if r is negative. And let's just compare to what we had what we saw in the previous slide. So we saw this series n equals, I forget if we started at 0 or 1. Yeah, so we started at, okay, so yes, so the series that we saw, we started at n equals 1 up to infinity and did 1/2 to the n. So here we're starting at n equals 0. So let me Yeah, so let me put a 0 down here. So this is equal to 1 over 1 minus 1/2, which is equal to 2. And that's what we had in the previous slide. We just had a 1 because we left off this first term, which is 1. And also, is the sum from n equals 0 to infinity of 1/4 to the n. We saw that one. That's 1 over 1 minus 1/4. So what is that? That is 1 over 3 quarters, which is 4/3. And that is, in the previous slide, we got our sum to be 1/3, but remember we started at n equals 1, so we left off that first term, which is 1. So if you remove 1 from here, you got 1/3, which is what we got before. Here's some examples. This first one, we are actually starting at n equals 1 instead of n equals 0. So I'm going to factor out so I'm going to write this as n equals 1 up to infinity of 1/10. Now let's do 3/10. That's going to be easier. Where's my pen again? 3/10 times 1 over 10 to the n minus 1. So I can factor this out. 3/10 n equals 1 to infinity of 1 over 1, or 1/10, the n minus 1. Now this thing here is a geometric series. So this is geometric series, and it starts at the n equals 0 power. So I always check and say, look, the lowest power of 1/10 is going to be, is going to be 0. So when n is 1, n minus 1 is 0. So using our formula, if you prefer, you can say this a, our constant, is going to be 3/10. R is the absolute value of r is 1/10, which is less than 1. So we know our our series is going to converge. So this thing now equals 3/10 over 1 minus 1/10. Let me erase that. I'm going to run out of room from the thing below. So that this is going to be 3/10 over 1 minus 1/10, and that is 3/10 over 9/10, and that's going to be 1/3. Okay, for this next one, we did this one, but let's use our formula. And I guess I did this using the formula before, but this one starts at n equals 1, so let me show you a slightly different way to get the same answer. So again, I want to write something that starts at the n equals 0 power, so I'm going to write this as 1/2 times 1/2 to the n minus 1. So I'm going to pull out the 1/2. N equals 1 up to, so this thing that I started with, you can think of it as the series that starts at 0, missing its first term, or you can think of it as the plain old geometric series that starts at 0 multiplied by 1/2. Either one works, but once we are here, now we have a equals 1/2, and absolute value of r is 1/2, which is less than 1, so this is going to converge, and it will converge to 1/2 over 1 minus 1/2, which is 1/2 over 1/2, which is equal to 1. Okay, this first one here, this third one here, this is n equals 1 to infinity. Well, this is obviously going to diverge. So let me write this as 2 times 2 to the n minus 1. So this is 2 times n equals 1. You know, I don't really need to go in all this detail. 2 to the n minus 1. So now here, well, let's be consistent. If a is 2, r equals 2, which is greater than 1. So this diverges. And that's clear, because this series is 2 plus 4 plus 8 plus 16 plus there, and there's no way that's going to equal anything finite. Okay, this last one. So here's one where r is negative. So let's actually write out what this thing looks like. So this is what is this equal to? This is n equals 1. This is so that would be negative 1/5. Then that's n equals 2. That's going to be positive 1/25. Then minus 1/125. And then plus, this raised to the 4th power is 1/625. And then I'm not sure I don't think I know offhand what. I'm just going to write plus minus, so something like this. Okay, so let's write this in our form. So this is n equals 1 to infinity of how do I want to write this? So this is n powers of negative 1/5. Is that correct? So let me write this as negative 1/5 times negative 1/5 to the n minus 1. So my a is equal to negative 1/5. My r, absolute value of r, is 1/5, which is less than 1. So this is going to converge. And this is going to converge to a negative 1/5 over 1 minus 1 minus r, which is negative 1/5. So this is negative 1/5 over 6/5. And so that's negative 1/5. Let's see, it's negative 1/5 times divided by 6/5 is times 5/6. I almost got that backwards. These are going to cancel, and this is negative 1/6. So it's really easy to make an off by 1 mistake here, or a negative sign error. So let's go back and check to make sure that this answer is believable. So I look at this series, and so the biggest term in magnitude is negative 1/5. So this dominates, and then I add something a little. Then I add a positive term that's a little bit to that. So let me sketch. So here's the number line. Here's 0. So I'm starting with negative 1/5. So my first term, I'm here. My second term, I'm adding 1/25 to it. I barely move over to the right. And then the next term I subtract. It's an even smaller thing, etc. So my next term, I go down here, and then I'm going to wind up sort of in this area. So I would expect the answer to be negative and a little bit larger, meaning a little bit closer to 0 than negative 1/5. And so negative 1/6 makes perfect sense. If I had gotten positive 1/6, I just do this, I check, and I know that cannot be right. So it's always good to check to make sure that your answer is actually believable and makes sense. So here's a series that is not geometric, and if I were to ask you if this converges or diverges, it should be obvious. You should say, well, it obviously diverges, but why? So let me just write that this thing clearly diverges. And well, note that for this series, if I take the limit, not of m, of n, if I take the limit as n goes in of the terms, this is just the limit as n goes to infinity of n, which is infinity. So, in other words, the terms, say an, do not go to 0. So, there's no way this thing can diverge, or sorry, can converge. We can make this into a theorem. It says, if a series converges, then the limit of the terms go to 0. And while this may seem like it's obvious, there are some subtleties. For example, let me do an example here. What if I have the series negative 1 to the n from n equals 0 to infinity? What if I have this series 1 minus 1 plus 1 minus 1? This is something which you may think some people may think it converges depending on how they group it. Like for example, let me group things this way. And you can say, well, this is clearly 0 plus 0 plus 0 plus etc. And so this thing equals 0. Well, someone else, well, let me rewrite this down here. So let me actually do one more term. Let me do plus 1, etc. So someone else may put parentheses this way. And they will say, well, this is equal to 1 plus 0 plus 0 plus equals 1. And depending on your views of life, you may just say, well, let's take the average of these two and equals 1/2. And as we will see, none of these are actually valid. So this test here says, if a series converges, then the limit of the terms has to go to 0. So that means obviously this diverges. Obviously this diverges, but also this one diverges as well, because the limit of terms do not go to 0. So a corollary of this is what's commonly called a divergence test, which is a quick test to see if a series doesn't converge. Is if the limit of an does not go to 0, or it doesn't exist, so for example here it does not go to 0, here the limit does not even exist, then your series diverges. And often for short we'll just write this as, again, if an does not go to 0. Okay, so let's do an example. Let's do two examples. This first one, the limit of this goes to 1 as n goes to infinity. If you want to formally verify that, that's by L'Hopital's rule. You can. This is an infinity or infinity over infinity in determinate form. So you can take the derivative of the top, which is 1, and the derivative of the bottom is 1 with respect to n. That is, of course. So this thing we can say diverges. This thing here is our next example is the harmonic series. These terms, these do go to 0. So we cannot use the divergence test to say it diverges. It's inconclusive. So let's write that down so that the divergence test doesn't apply. But we got to be careful. That does not mean just because these terms go to 0 does not at all mean that this series converges. So in other words, this series actually diverges. And that's something that you should just know, that this series diverges, but it is in no way obvious why this diverges, and it does not at all follow from the divergence test. So to summarize, this theorem says, if a series converges, then the limit of the terms goes to 0. So if you want to, I can write like that. And that works. But what fails is the backwards direction. The backwards direction fails. So it is not true that if the limit of the terms are 0, then the series converges. And the harmonic series is our first example of this. To better understand series, we need a new definition. A partial sum of a series is just the sum of the first k terms. So if we have an infinite series, we can just add up the first k of them, and we get the partial sum sk. And a basic theorem, and actually in advanced classes, this can even be taken to be the definition of convergence, but for now we'll take it as a theorem. A series converges to S if and only if the sequence of partial sums converge to S. So in other words, given a series, I'm going to do an example, but before I do that, let me do an example up here. Suppose I have a series like this. Doesn't really matter where I start. I could start at 0 or 1 or 18. So this is a series. From a series, we can get a sequence of partial sums. So I can get S1 plus, let me write this, let me organize this a little differently. I can write this as A1, or I guess A naught plus A1, A naught plus A1 plus A2, A naught plus A1 plus A2 plus A3, and what I get is this is S naught, this is S1, this is equal to S2, this is S3, next one is S4, and this thing here is a sequence of partial sums. So we can ask, does that sequence of numbers converge to anything? If it does, that's what the series converges to. And that should make sense if you think about, especially with that first example of when we had 0.33333, etc. How that equaled, that thing was equal to 0.3 plus 0.0. Actually, we didn't quite do it that way, but yeah. So with this series, how we wrote it in the first slide, I can write 1/3 as as the limit of the sequence, 0.3, 0.33, 0.333, 0.3333, and you can see how this sequence is going to converge to 1/3. Okay, so let's revisit that example that we did on the last slide, this alternating series. So now S1 is equal to 1, and I should say that there is a little bit of ambiguity as to in a series that starts at n equals 0. This is one reason why most of our series will start at 1. So the partial sum is sk is the sum of the first k terms. Well, so we could have this potential off by 1 error. Do we want, if we count S naught, or if we count A naught, then this second partial sum, or the first partial sum, S1, is the sum of 2 terms. So there's a slight potential for ambiguity. Typically, I'm going to say that SK is going to be all of the terms up to AK. So usually that's not going to include an A naught, but if there happens to be an A naught there, I'm not going to shift by 1. I'm just going to say everything up to AK. So let me actually clarify that. So all terms up to AK and inclusive. So don't worry about whether there's an n equals 0 term or not. Okay, so back to our example. The first partial sum is equal to 1. That's just this term. The second partial sum is equal to 1 minus 1 equals 0. The third partial sum is equal to 1. The fourth partial sum is equal to 0. And so the sequence of partial sums, SK, is 1, 0, 1, 0. And this does not converge anywhere. This diverges. And so this is another reason why this series, right here is not going to converge. Let's do two more examples, and you'll see that I've kept the statement of the theorem just for reference. This first example is we're revisiting example 2 from the first, I think the first slide. Oh, actually, hold on. I started at n equals 1, and I kept in this is my n equals 0 term, 1/2 to the 0, so I need to actually get rid of that. So let's get rid of that. Sorry, when I teach Math 4, our advanced calculus class, Math 454, I'm used to including the n equals 0 term. Okay, so here are partial sums. S1 is A1, which is 1/2. S2 is A2. Sorry, not A2, it's A1 plus A2. A1 plus A2 equals 3/4. That's just these two terms. S3 is A1 plus A2 plus A3. That's the sum of these three terms. That's which three? These three terms. And that's going to be equal to 7/8. And in general, you see the pattern here. S to the k is A1 plus is the first k terms, and that is equal to, what is that? 2 to the k minus 1 over 2 to the k. Now in terms of our box example, so the partial sum, so remember that we are filling in these boxes like this, and the kth partial sum is the total area that we have shaded. If you think about the frog analogy, the frog jumped into the wall. Remember that one? So the frog. So here's the wall, and the frog is halfway. The kth partial sum is the total amount of distance that the frog has. The total amount of distance that the frog has traveled in k steps. Okay, so notice that this sequence of partial sums converges. So let me write that down. So note SK is 1/2, 3/4, 7/8, and this sequence converges to 1, and therefore this did I say that right? This sequence converges to 1, and therefore this series of terms converges to 1 as well. It's easy to mix up the words sequence and series. Okay, so one more example is telescoping. So this is a series that's called telescoping, and it's should not be clear why I called it that, but if you take this fraction right here, if you take this and you do partial fraction decomposition, you didn't think that would come back so soon, did you? Use partial decomposition, you get that 1 over, so this fraction actually equals 1 over n minus 1 over n plus 1. I'll let you check that if you want to. So what that means is that this series, watch this, you're going to like this. This series, n equals 1 to infinity, is equal to 1 over n minus 1 over n plus 1. Okay, so what? So SK, so the kth partial sum is n equals 1 up to k of 1 over n minus 1 over n plus 1. And let's figure out what that is. So this is, at n equals 1, that's 1 minus 1/2. the next term is 1/2 minus 1/3. Then we have 1/3 minus 1/4. Let me, in the 1 minus 1/4, I'm trying to not run out of room, plus, and then the last term is going to be 1 over k minus 1 over k plus 1. So look what we have here. We have this 1, so these can come in pairs. This negative 1/2 is a 1/2 here, so those things cancel. Here we have the next two terms. We have a negative 1/3 and a positive 1/3. Those cancel. Everything else is going to cancel. The 1/4 is going to cancel. The 1 over k is going to cancel. And what we're left with, the only things that do not cancel, are this first term and this last term. So the partial sum quickly reduces down to 1 minus 1 over k plus 1. So this is called a telescoping series, because the partial sums, everything here goes out, and so the only thing left besides this 1 is it telescopes all the way to the end and picks up this last term. So this series, so this partial sum right here is clearly converges to 1. And by the way, when I put this arrow here like this arrow is just short for saying the limit as k goes to infinity. I think it's often easier to write an arrow. So what that means by this theorem up here, since the sequence of partial sums converges to 1, this series, how do I want to do this? This series converges to 1 as well.